Okay, so here I have a network analyzer that I purchased about 10 years ago for about 8,000 bucks. And what I have here is a 2.442 gigahertz, bandpass filter, 3-pole ceramic filter, and basically I've just put a 50 ohm load on it, and we're measuring the return loss on this guy right now. Now let's keep in mind it is at minus 18 dB return loss at 2.442. I want to show you that I'm going to get the same measurement using the TPI-1001-B. Also, what I'd like to do is measure the insertion loss of this device. Okay, I did not calibrate this cable out. There's probably, gosh, less than 0.3 of a dB. So I would say that the insertion loss is closer to 1.5 dB. But you can see the pass band, and it looks pretty good. It's flat. And so now we're going to do the same measurements with the TPI-1001-B. All right. So I can just simply take my RF output, and I'm going to sweep this guy, the same thing I did on this one, which was at 2.44 gigahertz with a 300 megahertz band. Or span, 300 megahertz span. Alright. Like I said, this is the first time I've ever done a video, so it may look a little awkward to you, but here we go. We got this set up. Now let's go look at the screen. Zoom in a little bit. Go to the Analyzer tab. Once again, I'm at 2.442 gigahertz or 2,442 megahertz. The span is 300, and I'm going to set the generator to 0 dBm. Because basically I want to see what the insertion loss is. It doesn't make any difference what this frequency is, because now the Analyzer tab controls the frequency. And if I hit start, we basically see the same response. I can put my cursor in here, and we got about a dB of loss here. So we're within a half dB of what the $8,000 unit says. And there you go. I mean, if I take this out to 600 and start. Oh, the other start. We can see what our rejection is at certain frequencies. The marker we can go to and say I want my 3 dB points. We can change the color. We can put this into memory, and there's a lot that can be done with this. So this is the forward motion, the forward mode. Now I want to show you the reflected mode. Of course, all plot data will be lost. That's all right. We've already plotted it. We didn't, but we would have. Now, there's a different way to set it up for reflected. Okay, so to set this up for reflected, I'm going to need to use a directional coupler. And here's a directional coupler, 800 megahertz to 2500 megahertz, which should work. I've got lots of different directional couplers. So I'm going to put this directional coupler in. At least try. There we go. We're going to measure the coupled port. The coupled port should be 10 dB down because this is a 10 dB directional coupler. Right now I'm not going to put my device that I'm testing in, but I am going to set the span back up at 300 just for comparison reasons. I'm in reflected. I'm going to do an absolute measurement, and you'll see that it's about 10 dB down, right? That's absolute. If I hit store and then go to relative, then it's basically done all the math and stored it, and now we've got a relative. I'm just going to leave that there. Now I'm going to plug my unit in, and let's just see the results. Okay, so it requires a few sweeps. Like I said, we could make this quicker by just taking less data points. Let's turn this 3 dB off. At the center, we were saying we were at about -18. So there, it's reading about -17, about -18. You can see that number right there. And you can see that it's very much very close to the expensive network analyzer. For Viswar, it's easy to get a Viswar reading 1.14 to 1. Here at where that wasn't matched as well, 1.62. So if we look at relative, we'll see that we had this hump. We saw that in the other unit as well. And there you go. For $400, you've got a signal generator, and you've got a analyzer. Of course, you're not going to get a Smith chart and get the complex numbers and for impedances, but for simple antenna tuning and looking for amplifier gain and filter response, this thing will work just great.